Hello everyone, my name is Anamadeen. I am the third member in this group project, which is AI powered based brain tumor detection system. So in this project my part is model building and training, performance optimization, training accuracy and loss. So let's dive into the model building section. So I am going to walk you through the model building phase of our brain tumor detection project using convolutional neural networks or CNNs. So in the model building, to accurately classify brain MRI scans into tumor or no tumor categories, we design a CNN model that extracts spatial patterns from image data. Let's dive into breaking the architecture step by step. First, we start with the input layer. It receives MRI images that are already pre-processed and resized to match the model's expected shape, in our case 240 by 240 pixels with 3 colors channels. You can see this in this implemented code. There is 240 by 240 pixel and 3 colors. Next we have convolutional layers. These layers act like feature detectors. They scan the image using filters to learn low-level patterns like edges, textures, shapes. After each convolutional layer, we apply pooling layers. These reduce the size of the feature maps and help keep only the most important information while reducing computational load. Once the important features are extracted, they are passed to fully connected layers. These layers help the network learn complex relationships and convert the spatial features into class probabilities. And finally, we use an output layer with a softmax activation function. Since we are doing binary classification between tumor and no tumor. In this project, we have also explored popular pre-trained models like VGG16, ResNet50 or MobileNet. These architectures are known for their high accuracy and were considered for transfer learning, which I am going to explain you next. All the above section I have explained you the architecture and the model building. We have later implemented it in our project that is available on GitHub. We will surely mention the link in the description below. So let's go into the improve model performance. So I'm explaining about the performance optimization. Now that we have covered how the model was built, let's talk about how we improve its performance using transfer learning techniques. Training a deep neural network from scratch can be slow and often requires a large data set. So instead of starting from zero, we use a popular technique called transfer learning. Here is how it works. We started with a pre-trained CNN model such as ResNet or EfficientNet, which had already been trained on a massive dataset called ImageNet. These models have already learned to detect common features like lines, edges, and textures. We reuse those layers to jump start our training process. The second is freezing layer. The next step was freezing the initial layers of the pre-trained model. Pre-trained model, that means we kept the original weights unchanged. These early layers are really good at capturing basic image features that are useful across many different tasks, not just brain scans. The third is fine tuning. Then we fine tune the later layers of the model. These layers were retrained on our specific brain tumor data sets. This allowed the model to adapt to domain-specific features like tumor shapes, textures, or anomalies found in MRI images. This method helped us get better results while saving training time and computational resources. By combining transfer learning with fine-tuning, we achieved a model that was both efficient and accurate in classifying brain tumors. Once our model was trained and optimized, we evaluated its performance on both validation and testing datasets to check how well it generalized to new unseen data. On the validation dataset, our model achieved a validation accuracy of 65.26% and with a corresponding validation loss of 0.6172. This gave us a good indication that the model was learning useful patterns without severely outfitting to the training data. On the separate testing, so in the conclusion we have mentioned that on the separate testing dataset, which the model never saw during training, we recorded our testing accuracy of 66.77% and a testing loss of 0.6082. These results show that the model maintained consistent performance and could generalize reasonably well to new MRI images. While the accuracy isn't perfect, it's a solid baseline given our dataset size and complexity. With further tuning and more diverse data, this model can definitely improve. More importantly, the results prove that deep learning can be a powerful non-invasive tool to assist in early detection of brain tumors. So that wraps up my part of the project. Thank you for watching. I hope this gives you a clear understanding of how we built, optimized, and evaluated our CNN-based brain tumor detection model. We will mention the GitHub link in our description section. Also, you can access the clip in the GitHub from the GitHub. Thank you for watching.